I recently built a hardware prototype using the Stewart Platform design, which is a really simple 6-degree of freedom parallel manipulator. And after solving the inverse kinematics, I realized it's actually quite simple, and I'm surprised that there isn't a better guide or Python package online. So I wrote both. Here is the Jupyter Notebook containing the explanations to the inverse kinematics, which you can find on my Github, as well as the Python package, which contains the same code. So if you want the full explanation, obviously this Jupyter Notebook is better, but let's have a quick overview first. So in terms of terminology, there is the top, which is the platform, the bottom, which is the base, and then this, which we call the leg, connecting the top and the bottom. And then there would also be this anchor points, which we literally call anchors. So there's an assumption, which is each leg connects a pair of anchors, and there would be 6 of these legs in total. Once you accept that, you will find that the inverse kinematics is really easy, because all you have to do is to rotate the top plate, which we call the platform, and then find the relative displacement between each anchor, and then that would be your legs. And you will also find that for each configuration of the top platform, there is only one set of valid leg length possible. Let's see a few more examples first. This particular configuration, where each anchor is a pair connected by a leg, and these apply for any translation and rotation as long as these legs can extend or shrink in length depending on where you need the top platform to be. So in the Jupyter Notebook, we also go one step further, solving the inverse kinematics using rotational servo motors. So to quickly go through this, first we define the bottom plate, these anchors, based on several parameters. After that, we plot it out to do a quick sanity check to see that nothing's too crazy. And then we define the rotational matrices, which is something you will have to study on if you have never seen this before. And then you would just translate and rotate the top platform here. And then you would have the relative leg positions. So these are essentially the vector for each leg. And then once you have the vector, you would take the normalized length of each vector, and that would be your leg length, which is the number that you have to command to your actuator in order to move your platform. The next section then talks about how to repeat the same process, except we substitute this leg of variable length with a servo horn and a servo rod, where the servo horn can be rotated. When I was studying this inverse kinematic, I found it very elegant and surprisingly easy to follow along, so I think you can too. And I've made sure that all my notations are consistent, and a lot of things are written in this note-like format, so I think you will have no problems understanding it as well. And this is all written in a Python class as well, as mentioned before, which you can find in this GitHub repo. I used this inverse kinematic solution to build a motion simulator. So all the information that's needed is available on this other GitHub repo, including the motion capture data, the STL files, as well as the BOM list. So if you found this helpful, please go and star these GitHub repos. I would really appreciate it. And good luck on your projects.